All right, what's good, everyone? Back for another day of learning journey. Of course, as always, got our curiosity with us, and we also have a cup of coffee with us too. Let me redock my chat so that I can see if anyone says anything. There we go. Nice. All right, without further ado, let's get into the Japanese portion of the day. I'm gonna start studying some hiragana. This is gonna be wa, ru, myo, right there. Bu, yo. Alright, easy money. Tap the gotcha machine, of course. This is going to be Shodu. Consult Google Translate, of course, our good old friend Google Translate. Shodo. Very cool. Alright, we're gonna keep on grooving and learning some hiragana. Or reviewing our hiragana. We have a shop. Beep. Noot right there. Go is right there. Ya. Ki. Rio is right there. Bo. This is gonna be red. Mu. Misclicked. Fuck, dude. Alright. Pet is right there. Kyo is gonna be right there. Mya. Pet. A. Niu. Tsu. To. Ro is gonna be that guy. You. Get. Got. I'm just not thinking right now. Myo. Zu. It's going to be Bu. We've got Pia, which is going to be this guy right there. Ya. Ju. Pi. Myo. Gyo. Jo is right there. We've got Cha. I almost said Chia, but Cha. Yo. Cho is right there. Zep. Zo. Pew. Yeah. Right there. Tap. Alright. Well, missed two. We would like to be better, but you know, it's okay. Yeah. And then Moot. We have got Kyo. Kyokatsuki. Is that what that is? Let's see. Kyokatsuki. And they're saying that translates to with. Interesting. All right, we're gonna learn hiragana, or we're gonna review hiragana again. We have. Oh, I wish I could do one mass review with like. I mean, I guess theoretically I could. Oh, it's right there. Nyo is right there. This is gonna be Byo. To. Zu. En. De. Ra. Yo. Ta. Ke. Cha. I. Sho. Kya. Ku. Ku. Nyu. Cho. Ryu. Ku. Ryo. Kyu. Ni. Wa. Gi. Z, Sa, Nya. Rat is that guy right there. Gu is gonna be right there. Te, Jo, Se, Yo, Mya, Bet. We got me. And last but not least, we have Ma. Alright, that's what we like to see. Straight hundos. Lovely. Tap our gotcha machine, of course. What is this? We have is that Fune? Let's see. Fune.
船
Fune. Okay, cool. Alright, one more. We have Nya, Ryu, Ki, Se, Kya, Go, So, Shi, Ga, Ho, Ba, Ta, Me. Messed up. Sheesh. Fu, Mu, Pya. Na is gonna be this guy right there. Ku, I, Chi, Nyo, Ma, Pe, Chi. Fuck, dude. Messing up. Gu is right there. Yo, Et, Do, Da, Yu, Ria, Wo, Pi, Yo, Su, Bu, Shu, Su. Alright. Missed two. We'd like to be better. Careless errors, really, for being honest. Can't change the past, though. Just got to keep moving forward and try not make the same mistakes. We have. Let's see. Oh, menu. Menu, I think that is. Menu.
メニュー
Menu. Pretty cool how that's similar in a lot of regards to its English counterpart. Let's move on to katakana. Let's study their settings, focused review. We're going to bump this up to 60 quiz size. Byo is going to be right there. Wo, Hyu, Et. This one's going to be Bu. Shi or Tsu. Tsu. Chi, okay. Ta is right there. Re. Su. Be. Te. So. Chu is going to be right there. Gi. Se. Ha. I. Let's see, this one is going to be Wa. A. Ga. Do is right there. De. This one's going to be Bu. Du slash Zu is right there. Ke. Gyo is right there. Go is right there. This one, Wo. Mo. Ro. N. Ba is right there. This one is going to be root. Het. Gu. Gu. Ki. Gu. Ka. Mi. Yu. Bi. Pi. Yo. Mu is right there. Da. Ria. Tsu is gonna be that one. Okay, cool. Bolt is going to be right there. Get is right there. Ryu. Kyo. Pa. Ryo. Alright, this is going to be Ma. Ku. Nu is going to be the number 7. Nyo is going to be that one. To. Chia or chop. Alright, we only missed one. That's pretty good considering we bumped up the size. So we'll take that for sure, ski. Alright, we're going to tap the gacha machine. This is Osorushi? Osorushai, something like that. Let's see. Osoroshi. Terrifying.
恐ろしい
Osoroshi. Okay. Alright, we're going to do settings, focused review. We're going to bump the number up to 60 again. Okay. This one, cheat. Wo. Wo. Zu. That. Chu. Yu. Nya. Ta. Ki. Sa. O. Nyo. Kyo. Gi. Pet. Cha is gonna be that one. Do slash zoo is gonna be right there. Is that Ket. So. Met. Pet. Ya is gonna be right there. Ga. U. Bio is going to be right there. I. I. Bu. Su is gonna be. Leave it some more vertical one. Nice. Okay. U is right there. Su. Ka is right there. Ryu. Kya. Ria. Ryo. Zo. Shu is right there. Ku. Ma. Bia is right there. Gya. This one is going to be Sha. Gyu. Mi. Pa. Ya. Za. Yu. Cho. Sa. Ri. Da. Q. Na. And last but not least, yo. All right, easy hundo. We'll take those every day of the week. Tap the gacha machine, of course. This is going to be choco. I assume that's like chocolate or cocoa. Choco, chocolate. Nice, very cool.
チョコ
Choco, okay. All right, and I think we're gonna cap off our katakana knowledge. At least every term we can learn, or not term, but letter. Okay. We've got beep. And then ya. Okay. Pew is going to be P, obviously. Okay. And then U. Okie doke. Pyo is going to be P plus yo, so P. Okay. And then yo. Alright, ja is going to be G, denoted, of course, by these quotation marks. And then ya. Okay. Jo is going to be G plus yo. Okay. And then yo. Okay, very nice. Pyo. New. Po. Pyu is right there. Pu is right there. Ja is going to be right there. Jo is... I almost misclicked. I almost messed up. Pia is right there. Very cool. Got 4 more terms to learn. This is like a Game Boy. Gamki. Gamuki. Is that what that is? Let's see. Gamuki.
ゲーム機
Gamuki. Okay. Game machine. Very cool. Alright. Ju is obviously going to be G plus U. Okay. And then U. Okay. Mia is going to be me. Okay. And then ya, of course. Alright. Mu is going to be me. Okay. And then you. Alright. And then last but not least, we have Mio, which is going to be me. And then Yo. Okay. Mia. Ju is going to be right there. Mu is right there. Mio is right there. Alright, easy hundos. We'll take that. Oh, it looks like something out of like Berserk or something. We have Uchu Ujin. Is that what that is? Uchi Yujin.
宇宙人
Uchi Yujin. Okay. Very cool. Alright, let's go into words. And we're gonna do settings because I believe we have 29. I will go with 30. Nice whole number. Alright. Cheap, inexpensive. Is that Yasui? It is very cool. Karuma is right there. Nichiobi is Sunday. Genki is lively. We have spare time, which is Hima. Nihonjin. Kore. Shinsetsu is going to be kind. Heya, or no, Matsui. Enpitsu. Isha, doctor. Muzokashi, it's difficult, hard, troublesome. Hansamu, it's right there. You is going to be Anata. Ashita is going to be tomorrow. Shiken is right there. Sushi. Koko. Famous, well known as Yume, which is right there. Pen is going to be that guy. We have Duyobi, which is Saturday. Busy, occupied is going to be Isogashi. Heya is flat. Oishi is going to be good tasting. Kaishain is going to be company office employee. Amerikajin is right there. Today is going to be Kyo. Takai is high, tall. And then student is going to be Gakusai. Okay, very cool. Easy 100. We will take those. Is that apricot? So we have Anzu. Okay. Just learn some Japanese basics. So we have, what is this? Des. Alright. And so this is Ashita, tomorrow. Is that Janai? Well, let's go. Show English translation. I am not free tomorrow. Tomorrow is going to be subject, so that's going to go first. So Ashita. And then we'll go. That's Hima. Oof, okay, we almost got it right.
明日は暇じゃないです。
明日は暇。
明日は暇じゃないです。
明日は暇じゃないです。This one is going to be, let's show English translation. Sushi is delicious, so sushi is going to be the subject. So that will be coming first. Sushi. Des. Wa in there. Hey, let's go.
寿司は美味しいです。
Sushi wa oishi desu. Alright. Next we have I am a university student. Oh, excuse me. Gakusai should go maybe first. Das last. Wa. What is this? Is that Reitashi? Ooh, I messed that up bad.
私は学
Okay,
生です。
Watashi. Okay. That's I. Obviously, that would be the subject, so that would make sense. Watashi wa.
私は学生です。
Watashi wa gakusei desu. Okay, and then next question. Okay. I am not free tomorrow. So would, let's see. Ashita wa Oof, okay, almost got it right. I think I did the exact same thing I did the first time.
明日は暇じゃないです。
Ashita wa hima janai desu. Okay. Gotta try and remember that. We have I am a university student. So watashi is gonna be first. Watashi wa desu. And then gakusai. Okay.
私は学生です。
Watashi wa gakusei desu. Alright. And then right here, if I remember correctly, we have. Oh, excuse me. I already forgot this, man. This is crazy. Like that. Oh, okay. That was kind of a guess.
明
But
日は暇じゃないです。
Ashita wa hima janai desu. Okay. Oh, they're trying to sell us Renshu Pro now. Ah, I see. Nothing's ever free in this world. Alright, this is going to be Yuki Daruma, I believe. Yuki Daruma is Snowman. Alright, we're going to do focused review. I learned recently. Okay. Alright, I am not Japanese, so Watashi wa what is this? Janai Nihonjin. Okay. I mixed them up.
私は日本人じゃないです。
Watashi wa Nihonjin janai desu. Okay. This is he is Japanese, so this is going to be like that. Okay, wait, let me process elimination. Des will come at the end. La is going to be right there. Or no, yeah, I think. So Japanese would not. Okay, so it'd be like that. Hey, let's go. Okay, slowly but surely starting to get it. And for
彼は
pronunciation,
日本人です。
kare wa Nihonjin desu.
彼は日本人です。
Kare wa Nihonjin desu. Alrighty. Okay, let's see. She is American, so start with des, and then of course wa, and then we have Kanojo, and then Amerikajin right there. Okay,
彼女はアメリカ人です。
let's hear it again.
彼女はアメリカ人です。
Kanojo wa Nihonjin, Kanojo wa Amerikajin desu. Okay. And this one is going to be wa right there. Nihonjin. Or no, Nihonjin might be right there. And then Janai. And that. Okay, very cool.
私は日本人じゃないです。
Watashi wa Nihonjin janai desu. Okay. 2 out of 3 ain't bad. And then we have. This is Fuin, I believe. Oh. Muffin is muffin. Okay. New vocab word unlocked. Join Renshu Pro today. What are they charging? $6.99 a month. Is kind of crazy work. I'll look into that later. Yeah, I guess that's where he stopped for right now. Watashi wa Nihonjin desu. Right. We're gonna go train ride at Matsuyama Castle. Actually, I kind of want to. Let me see. Open link in new tab.
皆さんこんにちは。ここは愛媛県の今治駅です。これから特急に乗って松山まで行きます。でも特急が出るまでにあまり時間がありません。すいません、特急って券買わないと中では買えないですか？
中は現金のみになります。
現金。
車掌に行っていただければ。
じゃあ乗っちゃっても大丈夫ですか？
車内で自由席でよろしい
I
ですか？
heard her spit that Genki. Hell
特急
yeah.
の松山までで。
はい。
はい、2番線の7から13番の間自由席になります。
はい、ありがとうございます。特急の中で切符が買えるということでした。ただ、現金しか使えないと言っていました。クレジットカードなどでは払えないという意味です。特急の電車が来ました。
特急
特急と
Express
いうのは普通の電車より速い電車です。乗りましょう。自由席なのでどこに座っても
free seat. That's going to be Juseki.
です。
Juseki.
特急に乗ると車掌さんが切符の確認に来ます。これはさっき改札でもらった紙です。これを車掌さんに見せて切符を買います。車掌さんが切符の確認に来ました。
失礼いたします。
はい、
ご来店いたします。
お願いできますか？
はい。今治松山ですね。
はい、
乗車券と金で1840円になります。
はい。車掌さんは切符を拝見いたしますと言いました。切符を見せてくださいという意味です。
大変お待たせいたしました。こちら切符になります。
はい、
I'm
あり
gonna
がとう
add
ござい
this to
ます。
watch later real quick because that
切
looks
符が買
interesting.
えました。私はずっと山を見ていました。ある時、ふっと右側を見たら海が見えました。でも気づいたのが遅すぎました。海はちょっとしか見れませんでした。次にこの電車に乗ったら
Fungini
絶対に
next.
右側に座ろうと思います。
And then I assume Kono is Densha's train. What's time? Okay.
松山駅に
Remains to be seen.
これから路面電車に乗ります。路面電車が来ました。 道路を走る電車を路面電車と言います。窓の外に緑が見えます。これはお城のお堀に植えられている緑です。お堀というのはお城の周りを掘って水を入れて
Moat.
敵が
That is Madi? Is that or Ohori? Let's see. I can't. Ohori? Yep,
お
there it is
城
right
に
there.
入れなくするものです。路面電車を降ります。
お願いします。はい、わかりました。
私はピッとやるのが下手です。この通りを行くとお城があります。みかんジュースのお店がありました。入ってみましょう。3種類のみかんの入ったジュースを買うことにしました。ジュースにするみかんを選びます。
じゃあ私、はるみが好きなんですけど、
今年春に出来が良くて、
はい、
甘かったんですよ。
はい。
これね、美味しいと思う。
じゃあはるみ。
はるみはみかんの
Harumi?
一種です。でも、はるみ以外はよく知らないみかんでした。
じゃあなんかおすすめのにしてもらってもいいですか？
甘めがいいですか？
甘め。
ちょっと苦みが入るか。
じゃあ苦めはなしで、酸味はちょっと欲しいです。
はい、はい、じゃあ瀬戸かはるみからなんで、
はい、
絞りますね。
ありがとうございます。
酸
Alright,
味
I'm gonna
というのは
add that to watch later as well because that looks pretty interesting.
例えばレモンは酸味が強いです。待っている間にジャムの味見をさせてくれました。
ありがとうございます。いただきます。
いろんなみかんのジャムがありました。
You don't
Are you
know?
having trouble trying to keep up with your professor? You've got to try Otter. Here's how it works.
みかんの
Yeah, I don't know what kind of
アイスも
targeted ad that
美
was
味しそう
about.
でした。
Graduated college like years
さ
ago.
っき味見したみかんのジャムです。いろんな種類のみかんがあります。そしてレモンも売っていました。レモン1個50円はものすごく安いです。
すいません。あとこれと、あとこのレモンお願いしてもいいですか？
じゃあ、もうちょっと入れておきますね。
わあ、すいません。ありがとうございます。
レモンを一つおまけ
Lemon?
してくれ
Lemon?
ました。
Hell yeah.
おまけというのは
Omake?
ただでくれたり
Bonus? Hell yeah.
安くしてくれたりすることです。これは頼んだジュースに入っているみかんです。このジュースとっても美味しかったです。今からお店の人があるおすすめを言います。それが何か聞いてください。
Who decide? He's gonna look at it, but it's all good. Your restaurant? Oh shit.
焼きおにぎりで100円で一食ですけど、
もう見えるとこですか？すいません。
うなぎって書いてる。
はいはい。
うなぎのおにぎりをおすすめしてもらいました。
onigiri,
買いま
rice
しょう。
ball.
こんにちは。今そこでうなぎの100円おにぎりがあるって聞いたんですが。あ、1個いいですか。はい。
一つだけ買ってみました。
あ、ごめんなさい。はい。ありがとうございます。はい、買いました。ありがとうございました。
Oh,
みかん屋さんの人が領収書を
What a
持
nice
って
person.
きてくれました。
いい匂いがします
that
ね。
was in America, they wouldn't
ありが
bat
とう
an
ござい
eye
ます。
at someone like
とて
forgetting
も
a
親
receipt.
切な方でした。
すいませんでした。
Different
ありがとうございます
levels to respectful cultures, I'd
というお
suppose.
店です。ぜひ行ってみてください。ところで、この辺で有名なのは蛇口から出るみかんジュースです。
Oh, that dude's got some panda dunked on.
蛇口
The influence of American culture is kind of crazy.
それぞれの蛇口から違う種類のみかんジュースが出てくるみたいです。でも私はみかんジュースを飲んだばっかりです。
Juice is, I assume, juice.
さっき違
Yeah.
う店で飲んだんで、また帰りにちょっと寄ります。はい、ありがとうございました。
これからお城に行くので、その帰りにまた来ます。ロープウェイ乗り場と書いてあります。ロープウェイに乗ってお城まで行きます。ロープウェイのチケットを買います。お金を入れて往復を選んで大人1人を選びます。往復は行きと帰りと
Fukua
いう意味です。
round trip.
乗り場3階と書いてあります。エスカレーターで上がります。
Escaleta.
もう一回エスカレーターで上がります。ここはロープウェイだけじゃなくてリフトもありました。リフトに乗ってみることにしました。私の番です。ドキドキしました。
That looks pretty fun. You for sure cannot have that over here in America. You'd have,
ものすごく
let's just call them lower intelligence individuals making an ass of themselves on it
ロー
for
プ
sure.
ウェイが通っていました。
はい。はい、ありがとうございます。
落ちなくてよかったです。ロープウェイを降りた後、お城までが遠かったです。ここに行きたい人は体を
Also
鍛
gonna
え
add
ない
this
と
to
い
watch
けませ
later
ん。
as well because it's pretty informative.
ここは松山城です。
Ooh, the Matsuyama Castle. Yeah.
松山城は1602年に建てられました。まずはチケットを買います。
Chiketto is that ticket?
あ、すいません。
Yes.
大人一人お願い。
お一人、
はい。
はい。支払うのね。じゃあ480円の。
はい、ありがとうございます。
お城で一番高い建物を
Yeah, that
天
was a
守
good
閣
stretch.
と言います。建てた時の天守閣が残っているのは日本全国で12のお城だけです。松山城はその一つです。今からその天守閣に入ります。ここで
All right, that might do it for this learning, not this Japanese portion. I was gonna say learning portion, but We still got a lot more to learn. We got the time today. I'm gonna light this up. Help boost the algorithm, of course. And yeah, so let's go to good old Khan Academy. We're gonna get our Mathematicas in, our mathematics portion of the day. All right. As you guys can see up here, I really didn't do that good last time because, yeah, I just got hit with some questions that I guess, I don't want to say the wording was weird, but the wording was just significantly different from what it, from the, like, videos and stuff. Yeah. All right, let's go into secant lines, challenging problem.
Consider the graph of the function f of x that passes through 3 points as
See if
shown.
I'm going to
these are
wuss
the
out
3
of
points
this
in
and
curve.
go to
Blue
another
is f of x.
subject.
Identify which of the statements are true. So they give us these statements. Let's see, this first one says f of negative a is less than 1 minus f of negative a over a. So this seems like some type of a bizarre statement. How are we able to figure out whether this is true from this right over here? So let's just go piece by piece and see if something starts to make sense. So f of negative a, where do we see that here? Well, this is f of negative a. This is the point x equals negative a. So this is negative a, and this is y is equal to f of negative a. So this is f of negative a right over here. And what we know about f of negative a, based on looking at this graph, is that f of negative a is between 0 and 1. So we could write that 0 is less than f of negative a, which is less than 1. So that's all I can deduce about f of negative a right from the get-go. Now let's look at this crazy statement. 1 minus f of negative a over a. What is this? Well, let's think about what happens if we take the secant line, if we're trying to find the slope of the secant line between this point and this point. If we want to find the average rate of change between the point negative a, f of negative a, and the point 0, 1. If this is our endpoint, our change in y is going to be 1 minus f of negative a. So 1 minus f of negative a is equal to our change in y, and our change in x going from negative a to 0. So change in x is going to be equal to 0 minus negative a, which is equal to positive a. So this right over here is essentially our change in x over our change in y from this point to this point. It is our average rate of change from this point to this point. So it is our average rate of change, or you could say it's the slope of the secant line. So the secant line would look something like this.
Yeah, it looks like my
like this. Slope of the secant line.
dropping
So this
some
right over here is
frames
slope
here. Apologies. I don't know why this is happening.
secant line between from negative a, f of negative a, to 0, 1. So just looking at this diagram right over here, what do we know about this slope? And in particular, can we make any statements about that slope relative to, say, 0 or 1 or anything like that? Well, let's think about what a line of slope 1 would look like. Well, a line of slope 1, especially one that went through this point right over here, would look something like this. A line of slope 1 would look something like this. So this line right over here that I've just drawn that goes from negative 1, 0 to 0, 1, this has slope 1. So this slope is equal to 1. So if this green line has a slope of 1, does this blue line have a slope? It clearly has a different slope. Is that slope, is this blue line steeper or less steep than the green line? Well, it's pretty clear that this secant line is steeper than the green line. It's increasing faster, so it's going to have a higher slope. So this, looking at it from this diagram, this blue line has a slope higher than 1, or the slope of the secant line from negative a, f of negative a to 0, 1, that is going to be greater than 1. So this thing right over here is greater than 1. So we're able to deduce this thing right over here is less than 1. This thing over here is greater than 1. So this thing is less than that thing. So this must be true. Now let's look at this one. We're comparing the slope of the secant line. We're comparing the slope of the secant line that we just looked at. So this is the same value right over here. So we're comparing this slope right over here to what's this? F of a minus 1 over a. Well, this is the slope of this secant line. This is the slope of this secant line that I'm drawing in this. Let me do it in more contrast. Let me do it in orange. That is the slope of this secant line. The slope of this secant line. So which one has a higher slope? Well, it's pretty clear that the blue secant line has a higher slope than this orange secant line. But here it's saying that the blue's slope is lower than the orange. So this is not going to be true. So this is not true.
So this is really just like visualization sort of deal.
Minus f of negative a over 2a. So this is the slope. Let me draw this. So this right over here, this is the slope of the secant line between this point and this point right over here. Our change in y is f of a minus f of negative a. Our change in x is a minus negative a, which is 2a. So this is the secant line right over here. So let me draw it. So this secant line right over here. So they're comparing that slope to this slope. F of a minus 1 is our change in y over a is our change in x. So we're comparing it to that one right over there. And you could immediately eyeball it, this kind of brownish maroon, I guess it's kind of a brown color. This secant line that goes all the way from here to here is clearly steeper than this one right over here. And we know that the average rate of change from here to here is going to be higher than the average rate of change from here to here, because at least from negative a to 0, we were increasing at a much faster rate, and then we slow down to this rate. So the average over the entire interval is definitely going to be more than what we get from 0 to a. So this one is also not true. This has a higher, we actually know that this is false. Both of these would have been true if we swapped these signs around. If this was a greater than sign, if this is a greater than sign. So this is the only one that applies.
Okay, that one, I like the visualization there. I feel like, and obviously I'm not going to know truly until I practice it, but from what I can tell, I kind of got that concept. Not completely understood, but grasped it a little bit, sort of deal.
Which points on the graph is f of x times f prime of x equal to 0? So if I have the product of two things and it's equal to 0, that tells us that at least one of these two things need to be equal to 0. So first of all, let's see, are there any points when f of x is equal to 0? So we're plotting f of x on the vertical axis. We could call this graph right over here, we could say this is y is equal to f of x. So at any point, does the y value of this curve equal 0? So it's positive, positive,
No.
positive, 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 positive.
Oh wait, yes.
But it is decreasing right over here. Well, it's decreasing here, then it's increasing, then it's decreasing. And it does get to 0 right over here, but that's not one of the labeled points. And they want us to pick one of the labeled points, or maybe even more than one of these labeled points. So we're going to focus on where an f prime of x is equal to 0. And we just have to remind ourselves what f prime of x even represents. F prime of x represents the slope of the tangent line at that value of x. So for example, f prime of 0, which is the x value for this point right over here,
Slope of
it's
the
going to be
tangent
some
line at that
negative
point.
value. It's the
Okay.
slope of the tangent line. Similarly, f prime of x, when x is
So
equal
then
to
it'd
4,
be b.
that's what's going on right over here, that's going to be the slope of the tangent line. It's going
Be
to be
obviously
a
b.
positive value. So if you look at all of these, where's the slope of the tangent line? 0. And what does a 0 slope look like? Well, it looks like a horizontal line.
Yeah.
So where's the slope of the tangent line here horizontal? Well, the only one that jumps out at me is point B right over here. It looks like the slope of the tangent line would indeed be horizontal, right over here. Or another way you could think of it is the instantaneous rate of change of the function right at x equals 2 looks like it's pretty close to, if this is x equals 2, looks like it's pretty close to 0. So out of all of the choices here, I would say only b looks like the derivative at x equals 2, or the derivative, or the slope of the tangent line at b, it looks like it's 0. So I'll say b right over here. And then they have this kind of crazy, wacky expression here, f of x minus 6 over x. When is that greatest in value? And we have to interpret this. We have to think about, what does f of x minus 6 over x actually mean? And whenever I see expressions like this, especially if I'm taking a differential calculus class, I would say, well, this looks kind of like finding the slope of a secant line. Whenever, in fact, all of what we know about derivatives is finding the limiting value of the slope of a secant line. And this looks kind of like that, especially if at some point my y value is a 6 here, then this could be the change in y value. And if the corresponding x value is 0, then this would be f of x minus 6 over x minus 0. So do I have 0, 6 on this curve here? Well, sure. When x is equal to 0, we see that f of x is equal to 6. So what this is right over here, let me rewrite this. This we could rewrite as f of x minus 6, over x minus 0, So what is this? What does this represent? Well, this is equal to the slope. This is equal, let me do this in a color. This is equal to the slope of the secant line between the points x f of x, and whatever the corresponding f of x is, and we could write it as 0 f of 0.
Oh, I
see.
see.
F of 0 is equal to 6. This right over here is f of 0. In fact, let me just write that as 6. And the point 0, 6. And the point 0, 6. So let's go through each of these points and think about what the slope of the secant line between those points are and point A. This is essentially the slope of the secant line between some point x f of x and essentially point A. So let's draw this out. So between A and B, you have a fairly negative slope. Remember, we want to find the largest slope. So here it's fairly negative. Between A and C, it's less negative. A and C, it's less negative. Between A and D, it's even less negative. It's still negative, but it's less negative. It's less negative. And then between A and E, it becomes more negative now. It becomes more negative. And then between A and F, it becomes even more negative. It becomes even more negative between A and F. So when is the slope of the secant line between one of these points and A the greatest? Or I guess we could say the least negative, because they're always there. It seems like they're always negative. It would be between point D and A. So when is this greatest in value? Well, when we're looking at point D. At point D, x is equal to 6. X is equal to 6, and it looks like f of x is like 5.5 or something. So this will turn into f of 6, which is 5.5, or maybe it's even less than that, 5 1/3 or something, minus 6 over 6 minus 0. That's how we'll maximize this value. This is the least negative slope of the secant line.
Okay. That was pretty interesting. Secant lines and average rate of change. So we're going to move on to another lesson, I suppose. I'm just going to look at this secant line with the graphs. Yeah, I might go back and like try and figure that out later, but I think
we're first exposed to the idea
we
of
have
a
15
slope
minutes
of a
on this
line
one.
early on in our algebra careers, but I figure it never hurts to review it a bit.
Quality isn't really that, or this audio quality here isn't really great, but
maybe I should call it my f of x axis. Y is equal to f of x. Let me draw my x-axis just like that. That is my x-axis. And let me draw a line. So let me draw a line like this. And what we want to do is remind ourselves, how do we find the slope? How do we find the slope of that line? And what we do is we take 2 points on the line. We take 2 points on the line. So let's say we take this point right here. Let's say that that is the point x is equal to a. And then what would this be? This would be the point f of a, where the function is going to be some line. We could write f of x is going to be equal to mx plus b. We don't know what m and b are, but this is all a little bit of review. So this is a. This is, and then the y value is what happens to the function when you evaluated it at a. So that's that point right there. And then we could take another point on this line. Let's say we take the point b right there. And then this coordinate up here is going to be the point b f of b, right? Because this is just the point when you evaluate the function at b. You put b in here, you're going to get that point right there. So let me just draw a little line right there. So that is f of b right there. Actually, let me make it clear that this coordinate right here is the point a f of a. So how do we find the slope between these 2 points, or more generally of this entire line?
y2
Because a line
minus
has
y1
the
over
slope is consistent the whole
x2
way
minus
through it.
x1.
And we know that once we find the slope, that's actually going to be the value of this f. But that's all a review of your algebra. But how do we do it? Well, a couple of ways to think about it. Slope is equal to rise over run. That, you might have seen that when you first learned algebra. Or another way of writing it, it's change in y over change in x. So let's figure out what the change in y over the change in x is for this particular case. So the change in y is equal to what? Well, let's just take, you can take this guy as being the first point or that guy as being the first point. But let's take, since this guy has a larger x and a larger y, let's start with him. So the change in y between that guy and that guy is this distance right here. So let me draw a little triangle. That distance right there is a change in y. Or I could just transfer it to the y-axis. This is the change in y. That is your change in y, that distance. So what is that distance? It's f of b minus f of a. So it equals f of b minus f of a. F of b minus f of a. That is your change in y right here. That's your change in y. Now what is your change in x? So we have the slope
this is
is change in y over change
pretty
in
self-explanatory.
x. Well, what's our change in x? What's this distance? Remember, we're taking this to be the first point, so we took its y minus the other point's y. So to be consistent, we're going to have to take this point's x minus this point's x. So this point's x coordinate is b. So it's going to be b minus a. B minus a. And just like that, if you knew the equation of this line, or if you had the coordinates of these 2 points, you would just plug them in right here, and you would get your slope. You would get your slope. That's straightforward. And that comes straight out of your Algebra 1 class. And let me just, just to make sure it's concrete for you, if this was the point, let's say this was the point 2, 3, and let's say that this up here was the point 5, 7. Then if we wanted to find the slope of this line, we would do 7 minus 3. So 7 minus 3, that would be our change in y. This would be 7, and this would be 3. And then we would do that over 5 minus 2. 5 minus 2, because this would be a 5, and this would be a 2. And so this would be your change in x, 5 minus 2. So 7 minus 3 is 4. and 5 minus 2 is 3. So your slope would be 4 over 3. Now let's see if we can generalize this. And this is what the new concept that we're going to be learning as we delve into calculus. Let's see if we can generalize this somehow to a curve. So let's say I have a curve. We have to have a curve before we can generalize it to a curve. Let me scroll down a little bit.
Yeah,
Actually, I
get
want to
them
leave this up here
curves.
just so show you the similarity. So let's say I'll keep it pretty general right now. Let's say I have a curve. I'll make it a familiar looking curve. Let's say it's the curve y is equal to x squared, which looks something like that. And I want to find the slope. Let's say I want to find the slope at some point. And actually, before even talking about it, let's even think about what it means to find the slope of a curve. Here, the slope was the same the whole time, right? But on a curve, your slope is changing. And just to get an intuition for what that means is, what's the slope over here? Your slope over here is the slope of the tangent line. The line just barely touches it. That's the slope over there. It's a negative slope. Then over here, your slope is still negative, but it's a little bit less negative. It goes like that. I don't know if I drew that. Let me do it in a different color. Let me do it in purple. So over here, your slope is slightly less negative. It's a slightly less downward sloping line. And then when you go over here, at the 0 point right here, your slope is pretty much flat because it's the horizontal line y equals 0 is tangent to this curve. And then as you go to more positive x's, then your slope starts increasing. Your slope starts increasing. I'm trying to draw a tangent line. And here it's increasing even more. It's increased even more. So your slope is changing the entire time. And this is kind of the big change that happens when you go from a line to a curve. A line, your slope is the same the entire time. You can take any 2 points in the line, take the change in y over the change in x, and you get the slope for the entire line. But as you can see already, it's going to be a little bit more nuanced when we do it for a curve, because it depends what point we're talking about. We can't just say, what is the slope for this curve? The slope is different at every point along the curve. It changes. If we go up here, it's going to be even steeper. It's going to look something like that. Something like that. So let's try a bit of an experiment. And I know how this experiment turns out, so it won't be too much of a risk.
Nice.
Better than that.
That's always good to hear.
So that is my y-axis. That is my y-axis, and that's my x-axis. X, and let's call this, we can call this y, or we can call this the f of x axis. Either way, and let me draw my curve again. So I'll just draw it in the positive coordinate like that. That's my curve. And what if I want to find the slope right there? What can I do? Well, based on our definition of a slope, we need 2 points to find a slope, right? Here, I don't know how to find the slope with just 1 point. So let's just call this point right here. Let's call that, well, that's going to be x. We're going to be general. This is going to be our point x. But to find our slope, according to our traditional Algebra 1 definition of slope, we need 2 points. So let's get another point in here. Let's just take a slightly larger version of this x. So let's say we want to take this, let's say we have that point right there. Actually, let me do it even further out, just because it's going to get messy otherwise. So let's say we have this point right here, and it's just h bigger than x. Or actually, instead of saying h bigger, let me just say h bigger. So this is x plus h. That's what that point is right there. So what are going to be their corresponding y coordinates on the curve? Well, this is the curve of y is equal to f of x. So this point right here is going to be f of our particular x right here. And maybe to show you that I'm taking a particular x, maybe I'll do a little 0 here.
And the y value associated with h plus x is going to be f of h plus x.
F of x naught. And then what is this going to be up here? This point up here. That point up here. Its y coordinate is going to be f of this x coordinate, which I shifted over a little bit. It's right there. F of this x coordinate, which is f of x naught plus h. That's its y coordinate. So what is the slope going to be between these 2 points that are relatively close to each other? Remember, this isn't going to be the slope just at this point. This is the slope of the line between these 2 points. And if I were to actually draw it out, it would actually be a secant line to the curve. So it would intersect the curve twice, once at this point and once at this point. You can't see it. If I blew it up a little bit, it would look something like this. It would look something like this. It would look like that, where this is our coordinate x naught, f of x naught, and up here is our coordinate for this point, which would be the x coordinate would be x naught plus h, and the y coordinate would be f of x naught plus h. Just whatever this function is, we're evaluating it at this x coordinate. That's all it is. So these are the 2 points. So maybe a good start is just say, hey, what is the slope of this secant line? And just like we did in the previous example, you find the change in x. The change in y. That'll be your change in y. And you divide that by your change in x. Let me draw it here. Your change in y would be that right here. Change in y. And then your change in x would be that right there. So what is the slope going to be of the secant line? The slope is going to be equal to let's start with this point up here just because it seems to be larger. So we want to change in y. So this value right here, this y value is f of x naught plus h. I just evaluated this guy up here. It looks like a fancy term, but all it means is, look, the slightly larger x, evaluate its y coordinate, where the curve is at that value of x. So that is going to be, so the change in y is going to be f of x naught plus h. That's just the y coordinate up here, minus this y coordinate over here. So minus f of x naught, and that's our change in, so that equals our change in y. And you want to divide that by your change in x. You want to divide that by your change in x. So what is this? This is the larger x value. We started with this coordinate, so we start with its x coordinate. So it's x naught plus h, minus this x coordinate. Well, we just picked a general number. It's x naught. So that is over your change in x. Just like that. So this is the slope of the secant line. We still haven't answered what the slope is right at that point. But maybe this will help us get there. So if we simplify this, so let me write it down like this. The slope of the secant, let me write that properly. The slope of the secant line is equal to the value of the function at this point, f of x naught plus h, minus the value of the function here, minus f of x naught. So that just tells us the change in y. It's the exact same definition of slope we've always used, over the change in x. And we can simplify this. We have x naught plus h minus x naught. So
just
x naught
be h.
minus x naught cancel out, so you have that over h. So this is equal to our change in y over change in x. Fair enough. But I started off saying I want to find the slope of the line at that point, at this point right here. This is the zoomed out version of it. So what can I do? Well, I defined this second point here as just the first point plus some h. And we have something in our toolkit called a limit. This h is just a general number, right? This h is just, it could be 10, it could be 2, it could be 0.02, it could be 1 times 10 to the negative 100. It can be an arbitrarily small number. So what would happen, at least just theoretically, if I were to take the limit as h approaches 0? So if, first maybe h is this fairly large number over here, and then if I take h a little bit smaller, then I'd be finding the slope of this secant line. If I took h to be even a little bit smaller, I'd be finding the slope of that secant line. If h is a little bit smaller, I'd be finding the slope of that line. So as h approaches 0, I'll be getting closer and closer to finding the slope of the line right at my point in question. Obviously, if h is a large number, my secant line is going to be way off from the slope at exactly that point right there. But if h is 0.000001, if it's an infinitesimally small number, then I'm going to get pretty close. So what happens? What happens if I take the limit as h approaches 0 of this? So the limit as h approaches 0 of my secant slope of, let me switch to green, f of x naught plus h minus f of x naught, that was my change in y, over my change in, over h, which is my change in x. And now just to clarify something, and sometimes you'll see it in different calculus books, sometimes instead of an h, they'll write a delta x here, where this second point would have been defined as x naught plus delta x, and then this would have simplified to just delta x over there, and we would be taking the limit as delta x approaches 0. It's the exact same thing. H, delta x, doesn't matter. We're taking h is the difference between one x point and then the higher x point, and then we're just going to take the limit as that approaches 0. We could have called that delta x just as easily. But I'm going to call this thing, which we're saying it equals the slope of the tangent line, and it does equal the slope of the tangent line. I'm going to call this the derivative of f. Let me write that down. The derivative of f. And I'm going to say that this is equal to f prime of x. And this is going to be another function, because remember, the slope changes at every x value. No matter what x value you pick, the slope is going to be different. It doesn't have to be, but the way I drew this curve, it is different. It can be different. So now, you give me an x value in here, I'll apply this formula over here, and then I can tell you the slope at that point. Now, it all seems very confusing and maybe abstract at this point. In the next video, I'll actually do an example of calculating a slope, and it'll make everything a little bit more concrete.
All right. So let's move on and watch this video.
So let's think about how we could find the slope of the tangent line to this curve right over here. So what I've drawn in red at the point x equals a. And we've already seen this with the definition of the derivative. We could try to find a general function that gives us the slope of the tangent line at any point. So let's say we have some arbitrary point. Let me define some arbitrary point x right over here. Then this would be the point x comma f of x. And then we could take some x plus h. So let's say that this right over here is the point x plus h. And so this point would be x plus h, f of x plus h. We can find the slope of the secant line that goes between these 2 points. So that would be your change in your vertical, which would be f of x plus h, minus f of x, over the change in the horizontal, which would be x plus h minus x. X plus h minus x minus x, and these two x's cancel. So this would be the slope of this secant line. And then if we want to find the slope of the tangent line at x, the slope of the tangent line at x, we would just take the limit of this expression as h approaches 0. As h approaches 0, this point moves towards x, and that slope of the secant line between these two is going to approximate the slope of the tangent line at x. And so this right over here, this we would say is equal to f prime of x. This is a function of x. You give me an x, you give me an arbitrary x that where the derivative is defined. I'm going to plug it into this, whatever this ends up being. It might be some nice clean algebraic expression, and then I'm going to give you a number. So for example, if you wanted to find, you could calculate this somehow, or you could even leave it in this form. And then if you wanted f prime of a, you would just substitute a into your function definition, and you would say, well, that's going to be the limit as h approaches 0 of every place you see an x, you replace it with an a. F of, I'll stay in this color for now, blank plus h minus f of blank minus f of blank, all of that over h. And I left those blanks so I could write the a in red. Notice every place where I had an x before, it's now an a. So this is the derivative evaluated at a. So this is one way to find the slope of the tangent line when x equals a. Another way, and this is often used as the alternate form of the derivative, would be to do it directly. So this is the point a comma f of a. Let's just take another arbitrary point someplace. So let's say this is the value x. This point right over here on the function would be x comma f of x. And so what's the slope of the secant line between these 2 points? Well, it would be change in the vertical, which would be f of x minus f of a over change in the horizontal over x minus a. So we'll do that in a purple color, over x minus a. Now, how can we get a better and better approximation for the slope of the tangent line here? Well, we can take the limit as x approaches a. As x gets closer and closer and closer to a, the secant line slope is going to better and better and better approximate the slope of the tangent line, this tangent line that I have in red here. So we would want to take the limit as x approaches a here. Either way, we're doing the exact same thing. We're having an expression for the slope of a secant line, and then we're bringing those x values of those points closer and closer together, so the slopes of those secant lines better and better and better approximate that slope of the tangent line, and at the limit, it does become the slope of the tangent line. That is the derivative of, or that's the definition of the derivative. So this is the kind of the more standard definition of a derivative. It would give you your derivative as a function of x, and then you can then input your x that you want, the particular value of x, or you could use the alternate form of the derivative. If you know that, hey, look, I'm just looking to find the derivative exactly at a, I don't need a general function of f, then you could do this, but they're doing the same thing.
Alrighty, we have 2 more videos to go, it would appear. So let's keep it moving and grooving. 1 more alternate form derivative.
Let's say,
or what did that say, for links?
Let's say that f of x is equal to the natural log of x, and we want to figure out what the slope of the tangent line to the curve f is when x is equal to the number e. So here x is equal to the number e. The point e comma 1 is on the curve. F of e is 1. The natural log of e is 1. And I've drawn the slope of the tangent line. Or I've drawn the tangent line, and we need to figure out what the slope of it is, or at least come up with an expression for it. And I'm going to come up with an expression using both the formal definition and the alternate definition, and that will allow us to compare them a little bit. So let's think about first the formal definition. So the formal definition wants us to find an expression for the derivative of our function at any x. So let's say that this is some arbitrary x right over here. This would be the point x comma f of x. And let's say that this is, let's call this x plus h. So this distance right over here is going to be h. This right over here is going to be the point x plus h f of x plus h. Now, the whole underlying idea of the formal definition of limits is to find the slope of the secant line between these 2 points, and then take the limit as h approaches 0. As h gets closer and closer, this blue point is going to get closer and closer and closer to x, and this point is going to approach it on the curve, and the secant line is going to become a better and better and better approximation of the tangent line at x. So let's actually do that. So what's the slope of the secant line? Well, it's the change in your vertical axis, which is going to be f of x plus h minus f of x minus f of x over the change in your horizontal axis. And that's x plus h minus x. And we see here the difference is just h over h. And we're going to take the limit of that. We're going to take the limit of that as h approaches 0. So in the case when f of x is the natural log of x, this will reduce to the limit as h approaches 0. F of x plus h is the natural log of x plus h minus
f of
the natural log of x, all of that over h.
Okay.
All of that over h. So this right over here, for our particular f of x, this is equal to f prime of x. So if we wanted to evaluate this, when x is equal to e, then everywhere where we see an x, we just have to replace it with an e. This is essentially expressing our derivative as a function of x. It's kind of a crazy looking function of x. You have a limit here and all of that, but every place you see an x, like any function definition, you can replace it now with an e. So we can, let me just do that. Whoops, I lost my screen. Here we go.
Bro got exposed in 4K there.
Right, f prime of e is equal to the limit as h approaches 0 of natural log, let me do the same color so we can keep track of things, natural log of e plus h, I'll just leave that blank for now, minus the natural log of e, all of that over h. All of that over h. So just like that, this right over here, if we evaluate this limit, if we're able to, and we actually can, if we are able to evaluate this limit, this would give us the slope of the tangent line when x equals e. This is doing the formal definition. Now let's do the alternate definition. The alternate definition, if you don't want to find a general function, derivative expressed as a function of x like this, and you just want to find the slope at a particular point, the alternate definition kind of just gets straight to the point there. So what they say is, hey, look,
okay, wait,
point, function derivative expressed as a function of x like this, and you just want to find the slope at a particular point, the alternate definition kind of just gets straight to the point there. So what they say is, hey, look, let's imagine some other x value here. So let's imagine some other x value. This right over here is the point x, comma, well, we could say f of x, or we could even say the natural log of x natural log of x. What is the slope of the secant line between those 2 points? What is the slope of the secant line between those 2 points? Well, it's going to be your change in y values. So it's going to be natural log of
over
x.
your change in x.
Natural log of x minus 1. Minus 1. Let me do that red color. Minus 1 over your change in x values. That's x minus e. X minus e. X minus e. So that's the slope of the secant line between those 2 points. Well, what if you want to get the tangent line? Well, let's just take the limit as x approaches e. As x gets closer and closer and closer, these points are going to get closer and closer and closer, and the secant line is going to better approximate the tangent line. So we're just going to take the limit as x approaches e. So either one of this is using the formal definition of a limit. Let me make clear that that h does not belong part of it. So we can either do it using the formal definition or the alternate definition of the derivative.
All right, pretty cool. Let's move on. I assume he's going to show us like a real working example here, as it says worked example.
The alternate form of the derivative of the function f at a number a denoted by f prime of a is given by this stuff. Now, this might look a little strange to you, but if you really think about what it's saying, it's really just taking the slope of the tangent line between a comma f of a. So let's imagine some arbitrary function like this. Let's say that is, well, I'll just write, that's our function f. That's our function f. And so you could have the point when x is equal to a, this is our x-axis. When x is equal to a, this is the point a, f of a. You notice a, f of a. And then we could take the slope between that and some arbitrary point. Let's call that x. So this is the point x, f of x, x, f of x. And notice, this top, the numerator right here, this is just our change in the value of our function, or you could view that as the change in the vertical axis. So that would give you this distance right over here. That's what we're doing up here in the numerator. And then in the denominator, we're finding the change in our horizontal values, horizontal coordinates. Let me do that in a different color. That would give you, so the change in the horizontal, that's this right over here. And then they're trying to find the limit as x approaches a. So as x gets closer and closer and closer and closer to a, what's going to happen is that when x is out here, we have this secant line. We're finding the slope of this secant line. But as x gets closer and closer, the secant line is better and better and better approximate the slope of the tangent line.
Yep.
Where the limit as x approaches a, but doesn't quite equal a, is going to be, this is actually our definition of our derivative, or I guess the alternate form of the derivative definition. And this would be the slope of the tangent line if it exists. So with all that out of the way, let's try to answer the question. With the alternative form of the derivative as an aid, make sense of the following limit expression by identifying the function f and the number a. So right here, they want to find the slope of the tangent line at 5. Here they wanted to find the slope of the tangent line at a. So it's pretty clear that a is equal to 5 and that f of a is equal to 125. Now, what about f of x? F of x. Well, here it's the limit of f of x minus f of a. Well, here's the limit as x to the third minus 125. And this makes sense. If f of x is equal to x to the third, then it makes sense that f of 5 is going to be 5 to the third is going to be 125. And we're also taking up here the lit as x approaches a. Here we're taking the limit as x approaches 5. So this is the derivative of the function f of x is equal to x to the third. So let me write that down in the green color. X to the third at the number x equals, at the number a is equal to 5. And so we can imagine this. Let's try to actually graph it just so we can imagine it. Actually, I'll do it out here where I have a little bit better contrast with the colors. So let's say that is my y-axis. Let's say that this is my x-axis. I'm not going to quite draw it to scale. Let's say this right over here is the point 125, or y. This is when y equals 125. This is when x is equal to 5. So they're clearly not at the same scale. But the function is going to look something like this. We know what x to the third looks like. It looks something like this. We know it's going to look something like this. So here our a is equal to 5. Our a is equal to 5. This point right over here is 5, 125. 5, 125. And then we're taking the slope between that point and an arbitrary x value. And an arbitrary other point on the curve. So this right over here would be the point. We could call that x, x to the third. We know that f of x is equal to x to the third. And let me make it clear. This is the graph of y is equal to x to the third. And so this expression right over here, all of this is the slope between these 2 points. This is the slope between these 2 points. And as we take the limit as x approaches 5, so right now this is our x. As x gets closer and closer and closer to 5, as it gets closer and closer to 5, these secant lines are going to better and better approximate the slope
tangential
of the
line.
tangent line at x equals 5. So the slope of the tangent line would look something, it would be even more, it would look something like that.
I feel like this is pretty self-explanatory, although it could be my prior knowledge. Derivatives coming in, because I did go to college. What derivative is described by the following expression, limit of as x approaches e, natural log x minus 1, okay, over x minus e, f prime e, so the derivative where y is equal to natural log x which derivative is described by the following expression. Let's see. Let me think my way through this. So this is y2, y1, x2, x1. So let me get out handy dandy Microsoft Paint here. And window capture this John. Properties. Oh, okay. Oh, I see. Gotta bring it up, I think. Actually, delete this source real quick. Okay. Add one. Window capture. Okay. Paint, capture method that. Okay, I should reset it. There we go. Bring it down a little bit. Okay. So our coordinates are going to be, let me bring this down on my screen. Our chords are going to be L, N. Oh, right, no, that's Y2. Okay, so we're going to do E, comma, -1. Ah, terrible penmanship. That's going to be our first one. And then our second one is going to be X, comma, L, N, X. Okay. So, as X approaches E, so it'd be F prime of E, since that's the point we're trying to find, where F of X equals, let's see, natural log X over X. Let's see, where F of X, okay, as X approaches E, where F of X equals, yeah, natural log X. Okay, cool. All right. Which of the following is equal to G prime pi for G of X equals cosine X? G is equal, so we're solving for pi. Okay, they all go to pi. Pi is going to be our x1 from the looks of it, which all these are correct. And then cosine of X, okay, wait, G of X, which would be another way of saying G of pi, the associated y value of pi is equal to cosine X. So we would do, obviously, all the denominators are the same. We would do cosine pi. Y2 would, or no, Y1 would be cosine pi, obviously. So we can rule out everything except for this one and this one. Cosine, okay, and then Y2 would have to be, that one. Oh no, that one? Okay. Alright, let me see the derivative function where x equals t, okay. Limit as x approaches t, g of x minus g of t, x minus t. We substitute g of x for cosine of x, so cosine x minus cosine t. Okay, that makes sense. Next question. Which derivative is described by the following? Limit as h approaches 0 of root 9 plus h minus 3 over h. So y2 would be root 9 plus h, and then y1 would be -3. And then as h approaches 0, so we do f prime 0, where f of x equals, let's see, root 9. This is y2. This would be f prime 0, where f of x equals, I don't think it'd be that. Let me think. Might not be the most entertaining thing. I'm just really trying to think through this. So we're saying root x would, that one? No. This one? No. Wow. Okay. root x plus let me see how they answered it. Expression is of the same form as in this problem is of the same form as the second expression, f of t plus h minus f of t over h. The numerator is is equivalent to root 9 plus h minus root 9. This tells us that root x, f of x equals root x. 2y1. Okay. So they're saying that y1 would be, oh, I see. Okay. Right here, f prime 1, f of x equals 1 over x. F prime is 1 over x, or no, y1 is 1 over x. And then f prime, as x approaches 0, f prime of 1 1 over x. So they're saying x is equal to 1 plus h. Okay, so this one wouldn't work, and this one wouldn't work, I don't think. Maybe. 1 over 1 plus x. I am mad confused right now, holy shit. Prime of 1. So the derivative of 1 when y is equal to 1 over x. Derivative of 1 when y is equal to 1 over x. 1 over 1 plus h. Okay, so I think it'd be 1 over x plus h, no? In the numerator. Because h would be the difference. No, maybe not. I'm gonna just do it. Yeah. I feel like he doesn't fucking prepare. Okay, I need to calm down. I just feel like these worked examples don't really kind of prepare you for these sort of questions. The derivative of function f at the point where x equals t is defined by the following two equivalent, f of x minus f of t over x minus t. So you can either use these two. Let's substitute f of x, or let's substitute y equals 1 over x and t equals 1. One over t plus h minus 1 over t. Let's see. Substitute t equals 1. 1 over 1. Okay. So we're just doing. Okay, I gotta redo that maybe. I'm fucking sucking ass right now. Oh my god. I suck at this. Prime of pi, where x equals I feel like I feel like the circuits in my brain are going haywire right now. Let's see. Fuck. Yeah, I might have to call it quits on this for today. I'm thoroughly confused, and yeah, I feel like my brain's just gonna implode. It's going pretty good up until I got to that exercise, and then just seems like they essentially pulled the rug out from under me. Let's move into how do graphics cards work? I feel like I've watched this before, low key.
My team's Gen AI tool helps you answer customer questions.
How many calculations do you think your graphics card performs every second while running video games with incredibly realistic graphics? Maybe 100 million? Well, 100 million calculations a second is what's required to run Mario 64 from
let me get the Microsoft Paint off.
We need more power. Maybe 100 billion calculations a second? Well, then you would have a computer that could run Minecraft back in 2011. In order to run the most realistic video games such as Cyberpunk 2077, you need a graphics card that can perform around 36 trillion calculations a second. This is an unimaginably large number, so let's take a second to try to conceptualize it. Imagine doing a long multiplication problem once every second. Now let's say everyone on the planet does a similar type of calculation, but with different numbers. To reach the equivalent computational power of this graphics card and its 36 trillion calculations a second, we would need about 4,400 Earths filled with people, all working together and completing one calculation each every second. It's rather mind-boggling to think that a device can manage all these calculations, so in this video we'll see how graphics cards work in two parts. First, we'll open up this graphics card and explore the different components inside, as well as the physical design and architecture of the GPU, or Graphics Processing Unit. Second, we'll explore the computational architecture and see how GPUs process mountains of data and why they're ideal for running video game graphics, Bitcoin mining, neural networks, and AI. So stick around and let's jump right in.
Pretty cool animations.
This video is sponsored by Micron, which manufactures the graphics memory inside this graphics card. Before we dive into all the parts of the GPU, let's first understand the differences between GPUs and CPUs. Inside this graphics card, the Graphics Processing Unit, or GPU, has over 10,000 cores. However, when we look at the CPU, or Central Processing Unit, that's mounted to the motherboard, we find an integrated circuit or chip with only 24 cores. So which one is more powerful? 10,000 is a lot more than 24, so you would think the GPU is more powerful. However,
they both serve different purposes, I'd assume.
A useful analogy is to think of a GPU as a massive cargo ship and a CPU as a jumbo jet airplane. The amount of cargo capacity is the amount of calculations and data that can be processed, and the speed of the ship or airplane is the rate at which how quickly those calculations and data are being processed.
So it's essentially efficiency versus volume.
A massive number of calculations that are executed at a slower rate versus a few calculations that can be performed at a much faster rate. Another key difference is that airplanes are a lot more flexible since they can carry passengers, packages, or containers and can take off and land at any one of tens of thousands of airports. Likewise, CPUs are flexible in that they can run a variety of programs and instructions. However, giant cargo ships carry only containers with bulk contents inside and are limited to traveling between ports. Similarly, GPUs are a lot less flexible than CPUs and can only run simple instructions like basic arithmetic. Additionally, GPUs can't run operating systems or interface with input devices or networks. This analogy isn't perfect, but it helps to answer the question of which is faster, a CPU or a GPU. Essentially, if you want to perform a set of calculations across mountains of data, then a GPU will be faster at completing the task. However, if you have a lot less data that needs to be evaluated quickly, then a CPU will be faster. Furthermore, if you need to run an operating system or support network connections in a wide range of different applications and hardware, then you'll want a CPU. We're planning a separate video on CPU architecture, so make sure to subscribe so you don't miss it. But let's now dive into this graphics card and see how it works. In the center of this graphics card is the printed circuit board, or PCB, with all the various components mounted on it. And we'll start by exploring the brains, which is the graphics processing unit, or GPU. When we open it up, we find a large chip or die named GA102, built from 28.3 billion transistors.
Holy
The
cow.
majority of the area of the chip is taken up by the processing cores, which have a hierarchical organization. Specifically, the chip is divided into 7 graphics processing clusters, or GPCs, and within each processing cluster are 12 streaming multiprocessors, or SMs. Next, inside each of these streaming multiprocessors are 4 warps and 1 ray tracing core, and then inside each warp are 32 CUDA, or shading cores, and 1 tensor core. Across the entire GPU are 10,752 CUDA cores, 336 tensor cores, and 84 ray tracing cores. These 3 types of cores execute all the calculations of the GPU.
Do they
and each has
execute
a
Order
different
66 though?
CUDA cores can be thought of as simple binary calculators with an addition button, a multiply button, and a few others, and are used the most when running video games. Tensor cores are matrix multiplication and addition calculators and are used for geometric transformations and working with neural networks and AI. And ray tracing cores are the largest but the fewest and are used to execute ray tracing algorithms. Now that we understand the computational resources inside this chip, one rather interesting fact is that the 3080, 3090, 3080 Ti, and 3090 Ti graphics cards all use the same GA102 chip design for their GPU. This might be counterintuitive because they have different prices and were released in different years, but it's true. So why is this? Well, during the manufacturing process, sometimes patterning errors, dust particles, or other manufacturing issues cause damage and create defective areas of the circuit. Instead of throwing out the entire chip because of a small defect, engineers find the defective region and permanently isolate and deactivate the nearby circuitry. By having a GPU with a highly repetitive design, a small defect in one core only damages that particular streaming multiprocessor circuit and doesn't affect the other areas of the chip. As a result, these chips are tested and categorized or binned according to the number of defects. The 3090 Ti graphics card have flawless GA102 chips, with all 10,752 CUDA cores working properly. The 3090 has 10,496 cores working. The 3080 Ti has 10,240, and the 3080 has 8,704 CUDA cores working, which is equivalent
That's kind
to
of crazy
having
to think about.
16 damaged and deactivated streaming multiprocessors. Additionally, different graphics cards differ by their maximum clock speed and the quantity and generation of graphics memory that supports the GPU, which we'll explore in a little bit. Because we've been focusing on the physical architecture of this GA102 GPU chip, let's zoom into one of these CUDA cores and see what it looks like. Inside this simple calculator is a layout of approximately 410,000 transistors. This section of 50,000 transistors performs the operation of A times B plus C, which is called fused multiply and add, or FMA, and is the most common operation performed by graphics cards. Half of the CUDA cores execute FMA using 32-bit floating point numbers, which is essentially scientific notation, and the other half of the cores use either 32-bit integers or 32-bit floating point numbers. Other sections of this core accommodate negative numbers and perform other simple functions like bit shifting and bit masking, as well as collecting and queuing the incoming instructions and operands, and then accumulating and outputting the results. As a result, this single core is just a simple calculator with a limited number of functions. This calculator completes one multiply and one add operation each clock cycle, and therefore with this 3090 graphics card and its 10,496 cores and 1.7 GHz clock, we get 35.6 trillion calculations a second. However, if you're wondering how the GPU handles more complicated operations like division, square root, and trigonometric functions, well, these calculator operations are performed by the special function units, which are far fewer, as only 4 of them can be found in each streaming multiprocessor. Now that we have an understanding of what's inside a single core, let's zoom out and take a look at the other sections of the GA102 chip. Around the edge, we find 12 graphics memory controllers, the NVLink controllers, and the PCIe interface. On the bottom is a 6 megabyte Level 2 SRAM memory cache, and here's the GigaThread engine, which manages all the graphics processing clusters and streaming multiprocessors inside. Now that we've explored this GA102 GPU's physical architecture, let's zoom out and take a look at the other parts inside the graphics card.
Excuse me.
On this side are the various ports for the displays to be plugged into. On the other side is the incoming 12-volt power connector. And then here are the PCIe pins that plug into the motherboard. On the PCB, the majority of the smaller components constitute the voltage regulator module, which takes the incoming 12 volts and converts it to 1.1 volts and supplies hundreds of watts of power to the GPU. Because all this power heats up the GPU, most of the weight of the graphics card is in the form of a heatsink, with 4 heat pipes that carry heat from the GPU and memory chips to the radiator fins, where fans then help to remove the heat. Perhaps some of the most important components, aside from the GPU, are the 24 gigabytes of graphics memory chips, which are technically called GDDR6X SDRAM, and were manufactured by Micron, which is the sponsor of this video. Whenever you start up a video game or wait for a loading screen, the time it takes to load is mostly spent moving all the 3D models of a particular scene or environment from the solid-state drive into these graphics memory
Interesting.
chips.
It's
As mentioned
the time
earlier,
it takes to load a game is
GPU
just
has
the
a small amount of
movement
data
time of memory.
storage in its 6 megabyte shared level 2 cache, which can hold the equivalent of about this much of the video game's environment. Therefore, in order to render a video game, different chunks of scene are continuously being transferred between the graphics memory and the GPU. Because the cores are constantly performing tens of trillions of calculations a second, GPUs are data-hungry machines and need to be continuously fed terabytes upon terabytes of data. And thus, these graphics memory chips
I'm gonna take a break and go use El Baño, the bathroom real quick. Be right back.
The same
Alright, and I'm back. Let's keep watching this video.
Time. Specifically, these 24 chips transfer a combined 384 bits at a time, which is called the bus width, and the total data that can be transferred, or the bandwidth, is about 1.15 terabytes a second. In contrast, the sticks of DRAM that support the CPU only have a 64-bit bus width and a maximum bandwidth closer to 64 gigabytes a second. One rather interesting thing is that you may think that computers only work using binary ones and zeros. However, in order to increase data transfer rates, GDDR6X and the latest graphics memory, GDDR7, send and receive data across the bus wires using multiple voltage levels beyond just 0 and 1. For example, GDDR7 uses 3 different encoding schemes to combine binary bits into ternary digits, or PAM3 symbols with voltages of 0, 1, and -1. Here's the encoding scheme on how 3 binary bits are encoded into 2 ternary digits, and this scheme is combined with an 11-bit to 7 ternary digit encoding scheme, resulting in sending 276 binary bits using only 176 ternary digits. The previous generation GDDR6X, which is the memory in this 3090 graphics card, used a different encoding scheme called PAM4 to send 2 bits of data using 4 different voltage levels. However, engineers in the graphics memory industry agreed to switch to PAM3 for future generations of graphics chips in order to reduce encoder complexity, improve the signal-to-noise ratio, and improve power efficiency. Micron delivers consistent innovation to push the boundaries on how much data can be transferred every second, and to design cutting-edge memory chips. Another advancement by Micron is the development of HBM, or the high bandwidth memory that surrounds AI chips. HBM is built from stacks of DRAM memory chips and uses TSVs, or through-silicon vias, to connect the stack into a single chip, essentially forming a cube of AI memory. For the latest generation of high bandwidth memory, which is HBM3E, a single cube can have up to 24 to 36 gigabytes of memory, thus yielding 192 gigabytes of high-speed memory around the AI chip. Next time you buy an AI accelerator system, make sure it uses Micron's HBM3E, which uses 30% less power than the competitive products. However, unless you're building an AI data center, you're likely not in the market to buy one of these systems, which cost between $25,000 to $40,000 and are on back order for a few years. If you're curious about high bandwidth memory or Micron's next generation of graphics memory, take a look at one of these links in the description. Alternatively, if designing the next generation of memory chips interests you, Micron is always looking for talented scientists and engineers to help innovate on cutting-edge chips, and you can find out more about working for Micron using this link. Now that we've explored many of the physical components inside this graphics card and GPU, let's next explore the computational architecture and see how applications like video game graphics and Bitcoin mining run what's called embarrassingly parallel operations. Although it may sound like a silly name, embarrassingly parallel is actually a technical classification of computer problems where little or no effort is needed to divide the problem into parallel tasks, and video game rendering and Bitcoin mining easily fall into this category. Essentially, GPUs solve embarrassingly parallel problems using a principle called SIMD, which stands for Single Instruction Multiple Data, where the same instructions or steps are repeated across thousands to millions of different numbers. Let's see an example of how SIMD, or Single Instruction Multiple Data, is used to create this 3D video game environment. As you may know already, this cowboy hat on the table is composed of approximately 28,000 triangles, built by connecting together around 14,000 vertices, each with X, Y, and Z coordinates. These vertex coordinates are built using a coordinate system called model space, with the origin of 000 being at the center of the hat. To build a 3D world, we place hundreds of objects, each with their own model space, into the world environment, and in order for the camera to be able to tell where each object is relative to other objects, we have to convert or transform all the vertices from each separate model space into the shared world coordinate system or world space. So, as an example, how do we convert the 14,000 vertices of the cowboy hat from model space into world space? Well, we use a single instruction which adds the position of the origin of the hat in world space to the corresponding x, y, and z coordinate of a single vertex in model space. Next, we copy this instruction to multiple data, which is all the remaining x, y, and z coordinates of the other thousands of vertices that are used to build the hat. Next, we do the same for the table and the rest of the hundreds of other objects in the scene, each time using the same instructions but with the different object's coordinates in world space, and each object's thousands of vertices in model space. As a result, all the vertices and triangles of all the objects are converted to a common world space coordinate system, and the camera can now determine which objects are in front and which are behind. This example illustrates the power of SIMD, or Single Instruction Multiple Data, and how a single instruction is applied to 5,629 different objects with a total of 8.3 million vertices within the scene, resulting in 25 million addition calculations. The key to SIMD and embarrassingly parallel programs is that every one of these millions of calculations has no dependency on any other calculation, and thus all these calculations can be distributed to the thousands of cores of the GPU and completed in parallel with one another. It's important to note that vertex transformation from model space to world space is just one of the first steps of a rather complicated video game.
Crazy people really thought about this and
we have a
designed
separate
this.
video that delves deeper into each of these other steps. Also, we skipped over the transformations for the rotation and scale of each object, but factoring in these values is a similar process that requires additional SIMD calculations. Now that we have a simple understanding of SIMD, let's discuss how this computational architecture matches up with the physical architecture. Essentially, each instruction is completed by a thread, and this thread is matched to a single CUDA core. Threads are bundled into groups of 32 called warps, and the same sequence of instructions is issued to all the threads in a warp. Next, warps are grouped into thread blocks, which are handled by the streaming multiprocessor. And then finally, thread blocks are grouped into grids, which are computed across the overall GPU. All these computations are managed or scheduled by the GigaThread engine, which efficiently maps thread blocks to the available streaming multiprocessors. One important distinction is that within SIMD architecture, all 32 threads in a warp follow the same instructions and are in lockstep with each other, kind of like a phalanx of soldiers moving together. This lockstep execution applied to GPUs up until around 2016. However, newer GPUs follow a SIMT architecture, or Single Instruction Multiple Threads. The difference between SIMD and SIMT is that while both send the same set of instructions to each thread, with SIMT, the individual threads
Looks like
don't
the
need
threads
to be
go at a
in
different
lockstep
rate.
with each other and can progress at different
Yeah.
rates. In technical jargon, each thread is given its own program counter. Additionally, with SIMT, all the threads within a streaming multiprocessor use a shared 128 kilobyte L1 cache, and thus data that's output by one thread can be subsequently used by a separate thread. This improvement from SIMD to SIMT allows for more flexibility when encountering warp divergence via data-dependent conditional branching and easier reconvergence for the threads to reach the barrier synchronization. Essentially, newer architectures of GPUs are more flexible and efficient, especially when encountering branches in code. One additional note is that although you may think that the term warp is derived from warp drives, it actually comes from weaving, and specifically the Jacquard loom. This loom from 1804 used programmable punch cards to select specific threads out of a set to weave together intricate patterns. As fascinating as looms are, let's move on. The final topics we'll explore are Bitcoin mining, tensor cores, and neural networks. But first, we'd like to ask you to like this video,
Sure thing.
write a quick comment below, share it with a colleague, friend, or on social media, and subscribe if you haven't already.
Whoa, I don't know how much that
dream of
is.
Branch Education is
A
to
lot of
make
money.
free and
Looks like at
accessible,
least
visually
€100
engaging
super
educational
donation.
videos that dive deeply into a variety of
Branch
topics on
Education,
science, engineering,
I would say
and
person,
how
but I'm
technology works.
sure it's like a
And
team,
then, to
given
combine
how
multiple
complex these
videos
animations
into
are.
an entirely free engineering curriculum for high school and college students. Taking a few seconds to like, subscribe, and comment below helps us a ton. Additionally, we have a Patreon page with AMAs and behind-the-scenes footage, and if you find what we do useful, we would appreciate any support. Thank you. So now that we've explored how single instruction multiple threads is used in video games, let's briefly discuss why GPUs were initially used for mining Bitcoin. We're not going to get too far into the algorithm behind the blockchain, and we'll save it for a separate episode. But essentially, to create a block on the blockchain, the SHA-256 hashing algorithm is run on a set of data that includes transactions, a timestamp, additional data, and a random number called a nonce. After feeding these values through the SHA-256 hashing algorithm, a random 256-bit value is output. You can kind of think of this algorithm as a lottery ticket generator, where you can't pick the lottery number, but based on the input data, the SHA-256 algorithm generates a random lottery ticket number. Therefore, if you change the nonce value and keep the rest of the transaction data the same, you'll generate a new random lottery ticket number. The winner of this Bitcoin mining lottery is the first randomly generated lottery number to have the first 80 bits all zeros, while the rest of the 176 values don't matter. And once a winning Bitcoin lottery ticket is found, the reward is 3 Bitcoin, and the lottery resets with a new set of transactions.
That's fucking
and input
crazy to think
values.
about. Holy shit.
So why were graphics cards used? Well, GPUs ran thousands of iterations of the SHA-256 algorithm, with the same transactions, timestamp, other data, but with different nonce values. As a result, a graphics card like this one could generate around 95 million SHA-256 hashes, or 95 million randomly numbered lottery tickets every second. And hopefully, one of those lottery numbers would have the first 80 digits as all zeros. However, nowadays computers filled with ASICs, or application-specific integrated circuits, perform 250 trillion hashes a second, or the equivalent of 2,600 graphics cards, thereby making graphics cards look like a spoon when mining Bitcoin, next to an excavator that is an ASIC mining computer. Let's next discuss the design of the tensor cores. It'll take multiple full-length videos to cover generative AI and neural networks, so we'll focus on the exact matrix math that tensor cores solve. Essentially, tensor cores take 3 matrices and multiply the first 2, add in the third, and then output the result. Let's look at one value of the output. This value is equal to the sum of values of the first row of the first matrix, multiplied by the values from the first column of the second matrix, and then the corresponding value of the third matrix is added in. Because all the values of the 3 input matrices are ready at the same time, the tensor cores complete all of the matrix multiplication and addition calculations concurrently. Neural networks and generative AI require trillions to quadrillions of matrix multiplication and addition operations, and typically uses much larger matrices. Finally, there are ray tracing cores, which we explored in a separate video that's already been released. That's pretty much it for graphics cards.
Very
We're
cool.
thankful to all our Patreon and YouTube.
It was extremely informative. Basically magic at this point. I completely agree. Alright, let's get into a little bit of C++ learning. today, or in yeah. All right. Gonna kind of use this as a sort of this tutorial as a sort of like
So you
kind
have
of
learned how to
introduction
declare variables
basic
and
thing.
constants. Now let's see how
Try
we
and
can write
wrap my head
mathematical
around
expressions
just how
by
the code
performing
works together.
calculations. This is where the fun
And
begins.
then I'm planning on, once we finish this, finding a course that has more like practice problem sort of deals and stuff. So yeah.
So I'm going to declare two variables, x and y. Now we can declare a third variable and set it to x plus y. So what we have here is called the addition operator, and x and y here are called operands. So now let's print z on the terminal. So std :: cout z. Take a look. So now we see 13. Beautiful. We also have subtraction, multiplication, and division. But division is a little bit tricky. In this case, because we're dealing with two integers, the result of the division is going to be an integer, even though in reality, dividing 10 by 3 is going to result in a number with a decimal point, which we call a floating point number in programming. So if we run our program, we see 3, but what if
So
you
it's
want to
just
see
gonna
a
round.
floating point number? Well,
Then you
changing
have to
the type
specify
of z
float.
to double is not going to solve this problem because, as I told you earlier, if both our numbers are integers, the result of the division is also going to be an integer. So to get a floating point number,
One
we
of
have
them has to be a
convert
float.
one of these numbers to a double. So
Oh, double.
take a look. First, the warning goes away. Now, if we run our program one more time, look, we get 3.3333. Okay? So this is how division works in C++. Now let me revert this back to integer and integer. Now we have another operator called modulus, which returns the remainder of a division. So what is the remainder of division of 10 by 3? It's 1. Let's verify it. There you go. Okay? Now, using these operators, we can modify our variables. Let me show you what I mean. So for simplicity, I'm going to remove y and z. We only have x, and we're going to print it on the terminal. Let's say we want to increment x by 5. Here's how we do it. We type x equals x plus 5. So first, this piece of code or this expression is going to get evaluated. The result is 15, and then the result will be stored in x. Okay? Now, similarly, we can subtract 5 from x. We can multiply x by 5, and so on. Okay? Now, we also have two more operators you need to know, and they are increment and decrement operators. So let's say we want to add 1 to x. We can say x equals x plus 1. That is totally fine, but there is a shorter and more concise way to write this code. We can say x plus plus. This is the increment operator. We also have decrement operator, but we don't have the equivalent for multiplication or division. Only increment and decrement, okay? Now, this increment operator, there are two ways we can apply it. We can apply it as a postfix, or
this may be the last ad you ever see, because with the free AdBlock extension from Capital One Shopping, you
as a prefix. Let me show you the difference. So I'm going to delete these two lines. Let's declare another variable called y and set it to x plus plus. If we apply this as a postfix, first, the current value of x, which is 10, is going to be assigned to y. So y is going to be 10, and then x will be incremented by 1. So if you run our program, x is going to be 11, but y is going to be 10. Let me show you. So we print x is 11, but if we print y is going to be 10. Okay? So let me add this as a comment for clarity. In this case, x is going to be 11 and y is going to be 10. Now, what if we apply the increment operator as a prefix? So we declare another variable.
Oh, I see why that works.
Plus plus x. In this case, because we applied this operator as a prefix, first, the value of x is going to be incremented by 1. So x is going to be 11, and then the result will be stored in z. So in this case, both x and z are going to be 11. Let's verify it. So if we print z, well, in this case, z is 12. I made a mistake because in the previous statement, we incremented x by 1.
Double
So if
incrementation,
we comment
essentially.
out this line, it's not going to get executed. So now, when we run our program, x is going to be 11 and z is going to be 11 as well. Let's verify it. So here's z, beautiful. And let's also print x. There you go. So here's what you need to take away. If you apply the increment or decrement operator as a prefix, first, this piece of code is going to get evaluated. So first x is going to be incremented by 1, and then the result is going to be stored in the other variable. In contrast, if we apply this operator as a postfix, first, the current value of x, which is 10, is going to be stored in y, and then x is going to be incremented by 1. Hey guys, Mosh here. I hope you have been enjoying this tutorial so far. I just wanted to let you know that this tutorial is the first hour of my complete C++ series, where you will learn everything you need to know from the basics to more advanced concepts. So watch this tutorial to the end, and if you still want to learn more, use the link below this video to enroll in the full course. The complete course contains 3 parts, each part being around 3 to 4 hours long, so you can complete them in a day or 2. You will also get a certificate of completion and a 30-day money-back guarantee. Again, if you're interested, the link is below this video in the description box. When writing mathematical expressions, especially the more complex ones, you need to take into account the order or priority of operators. Let me show you what I mean.
That PEMDAS?
So I'm going to declare a variable called x and set it to 1 plus 2 times 3. Now, let's print x on the console. What do you think we're going to get? Pause the video and think about it for a second.
You are going to get parentheses, exponents, multiplication, division, addition, subtraction. You're going to get 7.
The answer is 7. This is a very simple math question, but unfortunately, a lot of people get it wrong. Here's the reason. In math, the multiplication and division operators have a higher order or a higher priority. So when evaluating this piece of code or this expression, first, this part is evaluated. So 2 times 3 is 6. And then 6 is added to 1. So the result is 7. Let's verify it. So I'm going to run the program. There you go. We have 7. Okay. So here's what I want you to remember. In math or any programming languages, the multiplication and division operators always have a higher priority than addition or subtraction operators. But we can always change the order of these operators using parentheses. So in this case, if we wrap this piece of code with parentheses, first, this piece is evaluated. So 1 plus 2 is 3, and then 3 is multiplied by 3. So the result is going to be 9. Let's verify it. So run the program one more time. There you go. Okay. Now here's your exercise for this lesson. Take this mathematical expression and implement it in C++. Assume x is 10 and y is 5. So if you implement this correctly, z is going to be 1.3.
All right, let me pull VS Code here. File, new file. Math application, no. Exercise. Desktop. File. Okay. Here we do. So, be at least my attempt. We do what? IOStream or hashtag IOStream.
So positive.
Okay, let me go back to see what the basic setup is. Hashtag include, that's what I'm looking for. Hashtag include IOStream int main. Set up brackets. And then we would do, so let
Result
me,
is going to be implemented in C++.
so we said double. Double is the command for adding. And then st : C out. Okay. Just try. I'm probably gonna be wrong, but you know, so double. We do x plus 10 divided by parentheses 3 times plus 10 divided by 3 times y. Oh wait. Divided by 3 times y. Okay. And S T colon C out.
Multiplied by 3. So
X turn. Okay, what happens when I run this? What happens? This is not a C++. Oh, how do I do that? File. Okay, wait, let me copy this. Control C. File, new file. Yeah, let's see here. How do I set this? Debug? Can't debug. File, open file. What did we get? Oh, I think I have to save. Okay. Maybe not. I don't know. I'm just gonna.
the result is going to be 9. Let's verify it. So for S,
Just gonna have to see what he
y
does.
into x, numerator, y. But here's the tricky part. We have
Okay.
y. Here's the solution.
Yeah, I completely failed at that.
All right, here's the solution. I'm going to declare x and set it to 10. Then y, we set it to 5. And for z, first we have to add 10 to x. But we have to wrap this in parentheses because this whole thing is going to be our numerator. Once we have the numerator,
let me go back.
Then
So why are we setting these equal to this?
take this mathematical expression, then y, we set it to 5. And for z, first we have to add 10 to x, but we have to wrap this in parentheses because this whole thing is going to be our numerator. Once we have the numerator, then we're going to divide it by 3 times y. But here's the tricky part. We have to wrap this whole expression in parentheses because the result of this expression is going to be our denominator. If you don't use parentheses here, our denominator is going to be 3, and the result is going to be different. So we wrap this whole thing in parentheses.
I guess the reason
And
mine
now,
didn't work is you
let's
have to store the
print
variables.
C on the terminal, so we should get 1.3. Again, if you didn't solve this properly, don't worry, don't let that discourage you. Remember, you're a student, you're learning. If you know everything and you could solve every problem, you would be the one teaching, right? So don't let that discourage you, and let's move on to the next lesson.
Alright, that might do it for today's episode. My brain's kind of fried. I tried my best on that problem. Wasn't enough to get it right, but it's okay. It's all in the name of improving and learning. Kind of similarly to how the math portion of today went. I got absolutely cooked, and my brain got cooked as well. But it's okay. Your brain's a muscle. You got to break it down in order for it to grow. So yeah, with that out of the way, get out there, learn. As I always say, each day is a new opportunity to learn, and tomorrow's not guaranteed, so you got to make the most of the day. Anyways, with that out of the way, I realize I say that a lot. Have a good one.